don't share last class. Don't do. Huh? Should be in the group. Somewhere on the web? In contact. Can you share it with those who doesn't have it? Last week, round data.
It's round application.
Round application. Yeah, I sent by email, I sent only training testing tests, but there should be the whole folders containing also the pre-computed modules. Do you have it? Can anybody show me what kind of data you have from the last class? We need to know that to be sure. Okay, yeah, that's it. Do you have a signal? Okay. Okay. So you had this only workshop last class, so I should explain you. I should provide you with some theory. So remind you that we now in the classification part of analysis. So the first more than a half, I would say. Yeah, we spent considerable time doing regression. Regression predicting numbers. Now we do classification task, and we had started the metrics, so the metrics of evaluating the model performance are different, and okay, and to start the classification model, we're using the data. We're using the data from applied predictive modeling book, which is they use the interesting data set that in the past was used in the carbon competition, round data. So it's already 8 years old competitions, because it was not even 5 years ago, it's already 7 years ago, and 7 years ago data. Did you spend time of studying the data? Last class? Or you just went ahead? Okay. So what's the essence of the competition? The competition is to understand to whom university should give the money for the grant research. So the main task is to predict grant success or failure. And there is some experience to that. So the university, when you have money and people asking money for you, it's a question whether should I invest or should I not invest. And this is similar problem when you even for the investment task, right? So people writing applications and giving, okay, I will do this, this, and this, and then I will do this useful research, I will do this startup, etc. And then you don't know whether you should invest, you should trust, the application, or it's just waste of money. People are writing applications, but they are not capable to fulfill what they expect. And it's a difficult, you know, that the task is difficult by itself because it has a lot of non-numerical parameters, which should be converted to numerical. But the task is understand what factors that makes the grant successful. By successful grant, and if you will do science in the future, this is important for you too, because you know, when you apply, you have to comply with all the terms, dates, etc. So the funding agency, of course, would like to have success. But as a result, always there will be successful cases and unsuccessful cases. And here is the data, the real data from the U.S. University of Melbourne. This U.S. University of Melbourne collected data from 3 years, and the data which the structure of the data is very heterogeneous. So it's contained, these are names, these are just names: chief investigator, delegated researcher, principal supervisor, external advisor, if they exist and they can be a group of people or not, first of all, and then the role of individual listed on the class. So the total number of individuals are ranging from 1 to 15. And this is the first data, which is, you see, it's not numerical data at all. Then characteristics of each individual of the graph. So for each individual, there is a date of birth, home language, degree of the university, nationality, number of prior successful grants or unsuccessful, department, faculty status, level of seniority, length of employment, number of publications in different journals. So these are all behavior characteristics. You will see there will be a number of them. Then there are some internal codes. There is a code for research field, courses, discipline, and these are numerical values, RFSD codes. It may be some, you know, some field of research are more successful than the other. Then RSCD percentage, right? Then some other codes, codes of the area of research, because this is university. And American university, they have the whole range of disciplines. Not only, you know, the university is basic science, it's also included engineering department, technological department, even medical school. So, say university comprise the whole universe of what you can do. Then the last fields are designating submission dates of the grant, the monetary value of the grant, which is built into 7 groups. Some grants are, you know, small, some grants are large, grant category code, types of code, codes for the specific sponsor. I think it's very interesting the way we're starting it's the data. I think it's good for you to know that it's not only basic, you know, just tables with numbers, are subject to the modeling. For example, this case also reflects the case of medical applications. Some medical, when you now, if some of you will be developing something for personalized medicine, you will encounter the same problem. Even last year, a Kaggle competition, for example, was for one of the Kaggle competition. Was for classification of cancer samples based on the records of the doctors. So, for example, it's genetical test with some numbers, say level of something in the blood and presence or absence of this genetic variant. These are quite strict scientific factors and features. And also there is a description of the doctor of the patient, which should be somehow processed. So now, when in the age of big data, there is always a combination, or in any, say, psychology area, there would be many applications when a data scientist should consider processing words or qualitative information about some, even in science, I think it's in some areas, you know, some qualitative, not exactly quantitative. Of course, qualitative data will be converted somehow in numbers, but these are this what we have. This is what we have, and the original will now explore it as a table because you have it already as a table. Who doesn't have it? Who doesn't? Everybody have this run that, right? Run training test set. So, for example, how to deal with this data. Many fields are broken down for each individual, 15 columns for each individual, 14 individuals per grant. You will see there will be many binary predictors. For example, there are groups of predictors which will tell you how many investigators, right? So actually, with this kind of data, teaching engineering, this process, teaching that you have to somehow recompose images is very important task. And this feature engineering for this data set, specific data set, is done that some group of predictors are organized. How many investigators were the grants up by the role? Maybe groups of role-specific count variables, home language, nationality, degree, and collate. The number of non-zero percentages for each grant for the specific codes. Indicator for the month and date. Actually, this is interesting. Pay attention to this variable. There is a variable of the day of the week when the grant was submitted, and somehow it will show up as significance. Say grant submitted on Sundays more successful or vice versa than grant submitted on Monday, or during which period of the year. This is a schologically interesting thing. So, as a result, when the from the original data that can be downloaded from Kaggle site, I think still is, can be downloaded. There are that number, 1,784 predictors emerge as a result of teaching engineering. A lot of binaries, right? So there is a lot of binaries. The reason there is no such or that features. Let us look at this set. But when you investigate it for correlations, so you will find out that some pairs has more than 99% of correlation, and that is why many are near zero variance predictors. So, from this 1,000 original 784, predictors can be reduced to 1,000, which we will call full set, and 252 predictors that we call reduced set. So if you look at your data, right, that all these tables are saved in the package that you have about the grant application, and they have the names, specific names, full set and reduced set. Do you see this? Yes. You do. So you know now how, because all these are provided to you as our data type, so you can upload it as our data. So you have the command line from the workshop. Okay. So we will be trying, some will try the full set, and there is a script actually how to do it. There is a script. There is in data pair processing, there is a special technique which is called unsupervised feature selection. When you remove the fully correlated or you remove the features that are correlated with levels higher than a certain threshold, this is a supervised. Unsupervised, when actually you're removing features without knowing if they're correlated or not correlated, or have association or do not have association with the graph. Of course, you run before continuing when you do data analysis. It is very it is recommended to explore at least, well, it's difficult maybe to explore all 2000, though it is feasible. You can do it in an automated manner and see the outcome. But also what you can do, you can explore the one predictor that you feel that would influence the outcome. And this features, for example, number of prior success. For example, when you receive the grant and you see the person has already a number of successful grants. Yes, right? So this is a positive experience that actually could influence the next grant. And this is the dependence, how you can reflect it in percentage. This is, you see, this is actually, the black are number of successful, and red is number of unsuccessful, which is sorted by CI is chief executive, chief investigator. So the boss actually, who is the chief investigator. Here is the graphic, and you can see the percentage, right? So, for example, if there are no prior successful or unsuccessful grants, then the results of this grant, because it's a training set, and we have the statistic at least about one result, and this is, we see that this is the distribution. This is the ratio, which is actually changes when the chief investigator has at least one successful grant, or two successful grants, or three, or if the number of successful grants is more than, say, 8, there is no unsuccessful grant at all. So it's illogical, but you can exploit. You can exploit individual, as we did say the solubility data. We explore if you could see the dependence with others. So another interesting thing that comes out from this data is for 3 categorical predictors that have here is the one sponsor known or unknown. This is a contract value. There is a special characteristic that falls out, and the month of grant submission. This is January or other months. So if you look just on the numbers, just forget that right part. So look at the numbers, and you see that there is a grant, success or non-success, and you see this table, and from this table, one can calculate odds. First, of course, you can calculate percentage of successful or non-successful grants, right? Statistics. But what is interesting, not really the percentage per se, but what the odds ratio. Odds ratio is in statistics is a very interesting characteristic. And for example, with the odds ratio here, it's better to illustrate for the month. Say, look at this lower table rows, and you see that, say, successful grants submitted in January is this, 480 and 45 unsuccessful. While in other months is these numbers. The numbers tell you nothing, but then you calculate what is the percentage of all grants submitted in January is successful. And you go to the percentage. So 91% of all grants submitted in January are successful for some reason. And if you took all other months, it's only 43% successful in other months other than January. But then you can see the odds. The odds is what is the number of successful to unsuccessful. So you divide 480 on 45 and got this number. Or you divide this number by that list, and then you see the odds is 10. Odds for the month of January 10, so the difference, the ratio between successful and unsuccessful is 10. This is what we call odds. But the other ratio is even less than 1. So the ratio is less than 1, meaning that actually unsuccessful prevails here. So you see 43, less than 50%. And then when you see odds ratio, this is very useful for medical setup. Odds ratio is even 14 to 13%, almost 40. Not percent, it's 40. Odds ratio. So the odds ratio of grants being successful in January is 14 for the other months. This is gives you that there is some tendency. This is irregularity that you catch up. And this is easily to calculate. This is you can create a script that would process all your 2,000 predictors and generate your odds and odds ratios. And when you see odds ratios being high, even odds ratio 3 is significant. And then you can take out one by one important predictors, important features that make influence on classification. This is what you have.
Why did we take January?
No, they found out. So yeah, you have to guess somehow or see the plot the dependence of successful grants on month and see it. Just visually, the graph, the plot will really give you a hint. This is, of course, we know we don't. People spend time on exploring. Here is, for some reason already we can see by evaluating one by one, not as above, by one evaluation will produce you success rate. So how to create, this is another question, another issue that is inherent to this data is how to split and training. Why the university actually submitted it as a common competition. Just because you see the success rates over years. The success rate over years, you see, so the university give grants and only 45%, even less than 50%. So the success rate is very low, and it even went down in the year 2008. And this is a question. If there is something inherent to this year with such a fluctuation, you see, this is difficult. Maybe there is some factor that influencing this successful grant was somehow went down or reduced in the year 2008, and the data immediately feels it, or it's just a trend in the data. So the question is, when you have this data, how much data to take in the train test or the test set. So, for example, if grant success rate was relatively constant over the year, then the recommendation take all available data, right? So take all available data. And here is because we have this drop in success rates in the year 2008, maybe create models using the data before 2008, but still then based on how well they fit the 2008. And now if you look at your package of the data, you can see the training and test with these numbers, right? 2008, before or after. Do you see this? Huh? Do you have something indicating that's pre-2008 or not? I just want to be sure that we are sure. But do you have the data already? You might have the data. Pre-2008, yeah, you do. You see there is a pre-2008 data and year 2000. Did you find it? Did everybody find it? Pre-2008 data. What is it? Where is your package? The whole package, the whole that you have access to, the whole grant application. Where is it? It said that everybody has an access. Many files. Huh? Do you have it?
Yes, yes,
Okay, but can you have it also on the graph? Do you have it? Do you see it? 2006 and 2006, okay. Could you please hold it? Did you find it?
Yeah, I have the data.
Where is this?
Yeah, I don't know.
Because we will need it. No, you don't need to download it. Can you show me the whole, what kind of models do you have? Not models. Where is it on the web? The whole range of models that everybody shares. Okay, I want everybody to open this web page containing all the packages you have to download. Yes. Yes. It should be on your computer. You have this. You have pre-2000 data and 2008. Yeah, you do. Okay, I want to be sure that everybody has it. At least in France, they are first on the computer screen, and then the reason, yes, the reason I did not send it, well, it's too big to send by mail. The models, actually, I did send it by email too, only training data. I did not send modules because modules are big to be sent. Okay, that's fine. Did you locate them? No, the whole pack. Please, you have this one. Okay. Okay, so just to pay attention, I just want you to emphasize that why we'll be using this year 2008 or pre-2008, just for you to fix it. That's why, because 2008 has a drop in success rates, and that's why we will be dealing sometimes separately. And here is module 1. Module 1 is when the training set is almost 8,000 grants that include all pre-2008 data and 25 from the 25% from the 2008. So we don't want to exclude all 2008 years, but we will be we'll be testing on 75% of the 2008 data. This is the case to demonstration that it's not always straightforward, that you take all the set and randomly split it into the, say, 80, 20%, or 70, 30%. This is a demonstration that sometimes you should approach the modeling differently with some reasons behind it. So the reasons are different depending on the task of the model. So here is the training set in the pre-2008 data, test set in the 2008 data, and this is just straightforward. To see, this is, why is it done so? To see if there is, so here, if we could train the model of the, train the data model on the pre-2008 data, and then predict, considerably well the older 2008 data, then it is, you know, the factors that influence success or graph success exist already during all years. So, and the relative drop in the rate of success depends on the universal safety, universal factors. That's probably this factor just changed for some reason in the year 2008. And here is we also want to train on this 2000 years data. Okay, and for example, this already the result to see the difference. So the model one, when we can you comment on this plot? If somebody would show you this plot, can you comment on this plot? What's happening? So we have the classification model support vector machine, and this is say rock. It's not rock. It's area under curve actually. It's a tuning plot. It's a tuning plot, and this is the cost parameter. And here is two models, model 1 and model 2. What would you say? What's which modeling scheme is better? Which one you will use to actually the model is creating to decide now, you know, or computer decides whether to give you money or not to give you money, to support your grant or not to support your grant. So which model would you choose among these two models? Model 1, I remind you, model 1 is this one, model 2 is this one. So which one will you choose to make decisions on unknown data? Who can tell? Which one to choose to make decisions for unknown data? Huh?
More is better.
More is better, yes.
Or maybe model 2 with parameter 2 in the power. You see that the red line is maximum at some point.
Yeah, it has some maximum at some point. Model, you mean model 2, the red one. Model 2 that does not take into account $2,008. But you see there is a strange decrease in performance here, right? From model 2. This seems like more stable in prediction. This seems like more stable in prediction, and the our curve almost 88% is a good out value. It's a good out value. So the difference maybe is not considerable. Okay, this is a difficult question though. So once you, because yes, with fixed tuning parameter, you can say that this one is the best options, right? But when you see that it's kind of, the model is really, it's not as steady. It goes down quickly when tuning parameters. There is only one value that fits the highest value. And the model one is more steady. So depending with different cost parameters, it's have after certain thresholds, it have more stable thresholds. So it's a difficult task to decide which one is the best. So we'll see. Okay. You last class you were running how many models did you manage to run last class on this data?
3 or 4.
And which one? Did you write down, as I always ask, performance metrics?
No, and we didn't see the result of some of them because the computation thing.
No, but you don't need to do computation. You have to download one, and you didn't do predictions. Okay, I think we have to now repeat it. We'll see. Okay, the classification tasks start from logistic regression, right? Now, logistic regression, let me tell you. So it's like a linear model for classification tasks. So we start regression with linear modeling. Classification starts from logistic regression. Why is it logistic regression? Let me remind you some basic probability theory. The basic probability theory tells that here is observing H hats and H trials. So you toss the coin, and you have, say, you know, some number of heads, some number of tails. And the probability to see hats in a number of trials is binomial distribution. And this is the probability, which is when this is the probability to observe a hat, it's a p to the power 8, and then probability of observing a tail, 1 minus p. Then the number of observation of tails is n minus 8, and this is the formula. And let us see now, imagine that we look at this formula as a function. So it's not just the probability to observe. When we calculate probabilities, you always know what is the probability of a hat. Say if it's a pair coin, you toss the coin, and say if it's half and half, 50-50, you calculate probability. But now just imagine you don't know the probability of the coin. The probability is a function. It's like an x variable. And this is a function that depends on x. And the task is to find the maximum value of this function depending on the probability, to see when it reaches maximum, and what is the value of this probability. This is the task which is called maximum likelihood parameter estimation. This is the method that originally was proposed by Fisher 100 years ago. And the best explanation, to my point of view, is from on heads and tails. On heads and tails, when you plot them in a function. For example, imagine you toss 3 heads and 7 tails in one row, and here is the formula. And now you plot it, you plot the function. So when you see it, you do it because now your 7 and 8 are fixed. Let me draw it on the table. Let me draw it a little bit on the table. So you have a function which have a binomial because your n and 8 is fixed. So 3 heads, 7 tails. You can calculate this constant parameter, which is 7 factorial divided by 3 heads, 3 factorial by 4 factorial, and you get the number. Here you can cancel some value. Here is 1, 2, 3, 2 by 3, 6, so you have 35. You have 35, and then you plot as a function. So your functions of probability is 35 multiplied by probability to the power of h is 3, and 1 minus p to the power 7 minus 3, 4 here. Here you formula for your function, and this is the function. You can plot it. So now if you can submit it to the R, you can submit it to the MATLAB, it's not difficult. And when you plot this function as a function of y from x, so you plot it as a function 35 multiplied by x to the power 3, 1 minus x to the power 4. You plot this function, and here is the graph of this function. And this function has maximum. You have maximum. And if you look where is the maximum of this function, you can see that it's exactly coincide with the value. No, approximately, here is 1.30 something. It's not exactly 4, 0.4, it's 0.3 something, 0.3 something. And this probability is actually is 3/7. So if you divide it 3 by 7, it's approximately 0.4, 2 by 7, 20 by 7, 3, something like this. 0.43. So exactly the maximum of this function is exactly the frequency of observing hats. Is that clear or not? Where did you get this function? Here is binomial. So when you have you toss points, and you get 7 times 1, 2, 3, 7, and you got 7 tails, 3 hats, and 7 tails. So these are hats, these are tails. This is experiment. What is the probability to observe 3 hats in 7 trials? It's from the elementary probability theory. This is the probability to observe 3 hats in 7 trials is binomial distribution, and the probability to observe 3 hats and 4 tails. But probability over, if you have a probability to observe hat, the probability to observe tail is 1 minus p. Okay? This is probability to observe tail, this is probability to observe hats. So this is the formula from the elementary theory. But now I plot it as a function. So we have this fixed number. I calculated this coefficient. 737 is calculated by binomial coefficients like this. Number n factorial divided by h factorial, n minus h factorial. This is the formula, but I write it as a function of p, like this. So when it's 3 hats, as here, it's written here, 3 hats, here is 3 hats, 7 tails, it's actually, it's not 7 trials, it's 3 hats, it's almost 10 trials. I mislead it, but that's okay. So, or you can calculate it 3, here is 7, then there will be some constant number different, it doesn't matter. But this is a function, it's just a function, x, power function for x. And it always appears that the probability of the maximum falls on the frequency of hats. If you plot the same function for the 5 hats, 5 tails, the maximum falls on the 0.5, again, probability of hats. When you plot this function as 8 hats and 2 tails, so this is the maximum. Here is the maximum value. And the maximum value is, this is called a function, maximum likelihood function. Maximum likelihood function is its maximum at the point where p is equal to the proportion of hats. Here is proportion of hats, 3/10. This is the maximum parameter, the best parameter. So when your coin has a probability, that actually predicts parameter. If you observe 3 heads out of 10 trials, maybe your coin is so that it just produces these results. But here is the maximum likelihood estimated. It's not 1, it's just some values, because the whole area under the curve is 1. But then this is a maximum likelihood estimation. This is a method that is used in many applications of in statistics and in machine learning. It's called maximum likelihood parameter. So we estimate by this method that at that parameter your function reaches maximum, and then we provide this probability. Why I'm talking about this? Yeah. We here have a classification model. In classification models, you always have two coins, right? We have 2 classes, and 2 classes can be considered as head and tails of a coin. So you throw a coin and you have a head and a tail, and imagine if there is no inference, so it's just random events being granted. There is no dependency on the variables. There is no feature that influence success or unsuccess. It's just tossing a coin. It's just a random event for the grant being successful or unsuccessful. Then there is a formula to predict. Probability of the grant success. Because if you remember, in classification tasks, it's not only that we predict classes, like 1 or 2, we also predict probability. This is the probability of mail being spam. This is the probability of grant being success. This is the probability of a client to return your money. This is the probability that this protein binds to DNA. This is the probability that, this protein influence DNA folding, etc. For example, if the event is completely random, we can apply this binomial distribution. For example, in all pre-2008 grants, there are that number of grants, 6,000 something, and 3,000 success. Then you can write this formula for the successful, like head and tails in the coin, the same formula, and you can estimate it, make a likelihood estimate of this situation, and we got this rate. So this rate, the P would be estimated that this function, which is maximum, we know from this experiment, actually at the success rates of, at the rate of observing successful grants. Successful grants at 3,233, we divide it by the total number of grants, 6,633, and this is the maximum likelihood estimate. And here is, we describe just random process. We describe, but now we make the next step. We know that, our situation is not random, and there are some factors that influence this graph. And what we would like, so what is logistic regression? This is a formula of logistic regression. We say that log odds of the event, this is our assumption. So we take probability of successful grants, divide on the probability of unsuccessful grants, which is 1 minus p. We took logarithm to play with a little bit smaller values, and we approximate it by linear function. These are our features of prediction, the same we did in the, and that's why it's linear modeling for the classification tasks. And we modeling log, it's called log of the odds. This is odds threshold, or odds, right? Odds threshold. How much the probability of being successful is higher than the probability of being unsuccessful. And this is log odds is modeled by the linear function. linear predictor. This is the essence of the logistic regression. And then we can, when we have the formula with logarithm, we can just rewrite it. We take this, because it's logarithm, you take the exponents, say logarithm can be by the base, we love natural logarithm. And here is, we can just write an explicit formula for the probability. This is an explicit formula, right? So now we have, assuming that the loss-odds ratio linearly depends on the predictor, we have an explicit formula for the probability. It's produced probability of the event. Now let me, this is the modeling. This is modeling of the single predictor. For example, logistic regression models, when we model, here is probability of successful grant, and this is day of the year, right? Day of the year. And you see the distribution, which is not really linear at all. And this is maybe not a good idea. And this is log or single predictor, numerical day of the year. Let us come back to the workshop. Okay, let's move to the workshop. And I want you to get numbers, even if you did not get it from the last class. Let me open the workshop. And see what we can predict. As with linear model, I would like you to have blocks of code that can be quickly copied from Okay, let's see this logistic regression. So this is what you, this is show how you can download the raw data from the Kaggle sites. It's 8,700 run applications. Originally with 252 predictors. See, we made it, actually not we, but they made it. They made it to the 2000s because of this feature. This is what we didn't run in class, but there is a script. There is a script, create grant data as script. It can be downloaded from the chapter this applies to the book. I did run it myself. It took 1 hour and 3 course, so that's why you have already. So I prepared the data for yourself, and all for you, all the data would be just used in loads. You just have to specify the correct path where this data is located. Does everybody have this data loaded? And if you explore it as a table, you see just almost 8,000 rows. That's why it's kind of big. With the solubility data, we worked with around 1,000 rows. Now we have 200 variables. Now we have 8,000 rows with almost 2,000 variables. So there is a divisional testing and training like this. 8,000. You see, this is not 80-20%. Also, there is a pre-2008 data and year 2008 data. So if you look at these divisions, there is a different, just different divisions. Whether we took, it's two types of model that we will be dealing, and this is, we don't play, to my experience, to run this, if you have Mac or Unix, it does run well. You can use this function, just, for example, this worked on my Mac that have 4 cores, it's called Duo. Don't use, when you want to parallelize, you don't use all cores, all 4, because you don't want that your computer just hang on all 4 cores while doing compilation. You need at least 1 core for the other tasks, but it does not work on Windows. And to my experience, people who try to do parallelization on Windows always run into different problems. It's a little bit complicated, so if you want to play with the parallelization, do it alone at home for yourself. But it usually does work on Mac or Unix systems. It's not a problem. Okay, but we don't run it. Okay. These are what you should have done last class. Have you done this last class? Yes. Did I send around slides for the last 10? So you have this workshop. Good. So you can quickly reproduce it, right? You don't have to waste time on this. So this is, we're removing, this is what I explained. We're removing 99% correlation. Can you quickly execute it without wasting time? Because we're just repeating, because we did not get to the numbers, that's why we are repeating. But that should be quick. You just copy or you rerun the code from the previous class. Does it work?
Yeah.
Does it work? Does it work on you? You cannot run anything. Try. Okay. Do you know Python library? Okay. Okay, does it work for you? Okay, so let's come to logistic regression. Okay, we also remove near zero variance, right? So we remove the full set. No, we create near zero variance in the function we used in the regression block. So you can copy the slides. We remove near zero, and we're down to this is the result. Actually, I think I redistributed reduced set 3. Did I? Or not? Do you have this reduced set and full set R in the list of the run data packages? Yeah, so actually you do have it already prepared. So if you are lazy or this code for some reason does not work, you can what? You can load the reduced or full set directly from as an R data object because I provided it too. So as a data I provided training test pre-2008 years, 2008. And this reduces full set. Or you can also do it yourself. So for you to understand how it is done, you can see that reduced set, we just we remove some fields. So how we are down to the 252 predictors, this is a reduced set. Here is two, so this is what is written, that there is a chapters with code, but this is redundant. I don't use it. The book is provided with the codes for each chapter, and when you need to go deeper into the analysis, you can always look at the code used in the chapter, but it is more than we used during the workshops. So it is not necessary. That's why you can copy, but you must have it. Now, this is extreme control function. Trade control is how we train the data. It's the parameter that regulates the data training. And it has a different syntaxes compared to regression models. So in regression, here is the we emphasize that we have two classes. This is a special parameter. That plus probability is true, we will be always predicting probabilities and say predictions true, because this is just synthesis. Without say predictions true, the model won't calculate probabilities because it takes time. Then we do, here is logistic regression from carrot package. And to tell that, you see, we don't really tell whether it's regression or classification, but this metric and trait control will tell for itself. So once you have metric raw, it's it's like telling the command that the task is classification. And this line probably is not that long. I don't know if you manage to run it in class, or if it's too long, I must have it in the list as a model. Can you check? Did you manage to run it last class? Yes? Good. Then I would like you to predict. So this is the results, and you see there is it's a linear model, and there is no tuning parameter, because the result is just one row, which is nice. This is sensitivity and specificity, which also are not too bad. But I would like here. So you did it all, right? Now you have to write down the numbers. So you have start the table, and you will start the table, and on the list or in the file, we will be having all these metrics. All these metrics, which are core metrics. Here is the first for the linear regression model. We do, we start. We do area of the curve. We write down accuracy, sensitivity, and specificity on the test set. As with here, did we predict? What is predict? Here we do it's not on the predict. Okay, this is a back. So I want you. These are metrics actually. These are metrics for the training test. Remember, we created a block of analysis that you just copied and replaced with models. You remember this regression? So we have predict, we have train, then predict, then default summary. Remember, and you just copy. So for default summary, you create a table with predict, observed, false. I would like you to do now the same thing for classification models. So for classification models, we have the same. So you can use at the end any classification model, just substituting models and tuning parameters. To do so with classification, you need a train, the same train. Then you need predict. You have to predict and predict. Please modify. It's for linear discriminant. Please modify this logistic regression with predict. So we just run logistic regression function. Put here logistic regression. Used. So which data did we use for logistic regression? Reduce, right? How did we predict with the logistic regression? On reduce set. So you see, we reduce set is just a set of predictors to use. That's why it's here. We can always run the model on the full set or on the reduced set, right? So the syntax is when you have the square brackets, then empty space, then comma, then reduce space, meaning that reduce set is a vector that subselects predictor from all 2000 predictors. So the only 252. Only 252 is a subset. So you run this logistic regression. This is the first block. I will now go and check that everybody has it. Then you do predict on the test set. But test set also subsetting the reduced set, right? So you're predicting, and here is not LDA model, but the logistic regression model. Logistic regression model. And you use type probability true. Because we wanted to, we always want to have probability. This is the third line. The fourth line is, where is this? The fourth line is confusion matrix. And confusion matrix, just try to use correct data, correct reference yourself, not as on the disk. On the disk, we use the data from the trainer. Last year I wanted to modify the slide, but I forgot about it later because I want to predict on it. It's a little bit confusing now that we do it on train. But you can do it, so please, because you know there is a data and there is a reference. We did it actually in the previous workshop when we started the metrics for the classification models. When we start the metrics, so I want you now the confusion to correctly run confusion metrics on the predicted data and the raw Kauk metric also on the predicted data. This is all comes from the model. You see, this all metrics come from the models that we train. But this is not what I want. I want you to build the metrics on the predicted data. And tell me who is succeeded, and maybe share the code with everybody. No, it's not LDA. This is important. It's not LDA. LDA is a linear. We are in logistic regression. So there is should be you have to create the block of code. First, train, then predict, then confusion matrix, then raw curves. How's it going? Not as on the desk. No. You have to do it yourself. So you can. Which one? Which have you completed the one I asked? Where is logistic regression? I guess they're talking about logistic regression. Can you give me the numbers then? Or you haven't thought? Are you just doing something? Then I want you to do first train, predict, confusion matrix, rock curve, logistic regression. No. This is what you've done. This is you've done for the train set. I want you to predict on the test set. So you have to try. There is no on the slides. You have to think. Prepare yourself. Don't worry. Not yet. Okay, I see. Okay, people thinking. No, there is no. It's not on the slides. You have to do it yourself. You can consult, predict from the LDI. Okay. I want you to do it yourself. You do not copy. You can copy it, but copy thinking what you are doing. Okay. Did everybody at least what was on the slide was here? This works, right? Did it work for everybody? Or it did not. What problem? What is the problem? Okay, we train the model. What's the object? Okay, let me change glasses. Okay, I'll help. After that, you do predict. Predict on the test set. You train on the train, and you predict on the test. Predict like this. But not on linear discriminant. Put here logistic regression model. Not LDA. We did not count it. Huh? What? Не работает? Okay, fine. Good. With this one actually, with type probability. Okay, then this is the first step. Predict with the not LDA, not linear discriminant analysis. No, logistic regression. Predict logistic regression, and now use confusion matrix and raw Hauk and build raw Hauk for the test data. Go back to the one slide back and see how did we run confusion matrix and our curve for the evaluation of matrix performance. Predictions true. Okay, here is predict but logistic regression. Did it work? Did predict work for the test set? Let me see one by one. Did it work? Predict, okay. You predict this model, the test is testing, but square bracket reduce set the same, yeah. You said that means you take subselection for columns. And you want type probability. Type equals prop. You want also to predict prop. Okay. Logistic regression. Now confusion matrix, this is not from the model. That's the problem. Okay, people having problems with confusion matrix. Who managed to find out? Do you have the code from the previous slide? Yes. From the previous class for confusion matrix? Not from the last class, from the class before, from the 9th. Do you have a code? Your own? And let me see for the computer. Where do you have confusion from? So we run to campaign. Oh, here. You see what we take? Class objects. from the test and reference or its response for the or reference the other class from the simulated test. So we have the should be exploit value. So we have our testing sets. Does it contain does it have the class column somewhere? Первоначально, да, в смысле, это на которых мы сейчас тестируем, тренинг активности. The testing table should contain class column. Try if it's there. Try to maybe print it. Testing. Type here, testing dollar class. Yes, there is. So this is your class column. So when you see it, this is successful and successful. So there is a column in your set that is true. So it would refer to the reference, right? It's a reference because we know for sure it is. Now we have what we predicted. We have object that we predicted, and the object that is predicted, it's actually, yeah, you have to run twice. So you see on the linear discriminant analysis, we run this prediction twice. Once to predict classes, the other to predict probabilities. And the result is just a vector. The result is just a vector. Can you come back to the current workshop? So here, if you explore what is this MR test, you explore what is there. MR test. It's just vectors containing consistent. So if you type it, here it is. It's just, well, yes, two vectors, one containing successful probability and the other unsuccessful, but they sum up to one. They usually sum up to one. This is because it's maybe better to name as LF test probe, as I did in the probes, you see, and then separate and predict classes. Actually, you have to run it. You have to run predict twice. The one without using type probability, when get back to these classes, and when providing type probability, you will predict probabilities. So, who managed to run finally confusion? How's going? How's going? Вы сейчас где? Ну так сильно.
Не, ну не сильно, ты не запомнишь.
Так, что у вас получается? Смотрите, почему я делаю? У нас был магистр прибрежья. Модель такая. Давайте с магистром прибрежья. Вот, хорошо. Ну, тогда здесь тоже вот магистр прибрежья. Ой, я пропустила. Хорошо, вот давайте проявляем. Где отделить? Следующий шаг. Ну, давайте, оставьте, вам пригодится. Давайте сделаем смотрите, ну, давайте его подсоединим, начнем делать. У нас есть модель. Теперь вот после этого после этого вы представляете, да, вы запускаете, как вы представляете, тест-классы, как вы представляете, теперь я хочу Fusion Matrix и вот. У меня есть workshop 9, который должен вам представить. Как мы это делали, сначала где куда классы, куда пробовали. Там есть строк, по-моему, преподобный. Да, отлично, надо смотреть. А он называется по-другому, да. Он называется okay, I'm sorry I forgot about the break. You take a break now. This was a difficult task. We'll show you the good solution. Sorry, unfortunately, I don't have it on the desk, but that's why I thought you would go through. Okay, so now I want you to run Fusion Matrix and library walkout from but not from the predicted value. So we'll show you the right solution soon. Let's finish. I suggest let me finish the logistic regression, then I'll make the break. Это работает. Отлично. Так, у вас тест-класс, reference. Это из этих классов. Давайте подключим ваш проект. Так, еще надо walkout. Да. Нет. Это я подтверждаю. Надо из теста. Да, то есть первый response – это то, что мы наблюдали. Нет, мы наблюдаем тест. Наблюдаем тестинг класс. Да. Все правильно. Предикция. Пробы есть. Да. Response class, level class, response testing class, там знаете что, там две колонки. Mmda Forbes, сделайте первую, там две колонки. Он говорит, что он понимает это последствия. Или можно, знаете, как через голос сохранить именно. Например, okay, we have the good code to share with you in the group because maybe you have to. Хорошо. Теперь мы представим. Это модель. Модель предел класса. Представляли классы. Представляли проведение. Отлично. Теперь берем отжимаем. Значит, смотрите, давайте возьмем, у вас есть вот дело. Отжимаем, где-то там институционная модель решения, вот которые есть, которые нет, у нас было два компьютера, и мы тестировали да, это то, что пользуется, они у вас тестинг класс. Да, это старое, это референс, и это очень много писать. Много Пошлите мне, пожалуйста, кусок кода по e-mail. Можно? Я его потом, я не забуду, мне надо слайды обновить. Да, значит, да, первое, response, у нас Значит, здесь вот видите, разные модели. Первая получится successful, он probability целую таблицу. Здесь, чтобы достичь probability, вы берете доллар и пишете success. Сейчас я покажу на экране. А вы поняли, да? Вы тоже сейчас... Did you send me? I just... Not yet. Not yet? Please drop. Yeah, не надо. Вот надо поправить. То есть, окей. Где логистика решена? Где она осталась? Нет, это не нет, logistic regression. Logistic regression. Let me show. It's time to show the solution on this page. Did you send? Or maybe we can put on it. Can we? Do you have a mark or do you have this? Can we show the solution quickly?
I sent it to everybody.
You already sent it. Did everybody saw a solution? This is important. That's why this is important for us now because we will have in a moment block of analysis that we can reuse and reuse depending on the model. That's why I want you to show you. I'm waiting to get the solution on the screen or by mail to put it on the screen. So you predict did everybody see the solution on in the group or somewhere? Did you send? Okay. Just one moment, and I'll show you, and I'll show it on the screen. One moment.
Нижнее у тебя будет сравнение, да?
Да.
One moment will show. This is important to have this block of analysis. So you do the same as in regression. You do your modeling, you train. As a result, you have a model and you predict. But here you predict twice. Once you predict classes, and secondly you predict probabilities. And then that's it. Then you run confusion matrix. You have predicted classes, and for the confusion matrix, you need classes. For the raw curve, you need probabilities, because if you remember the video from the last or before last class, nice video which you can report on the screen. You plot this raw curve. Playing with the threshold classification for probabilities. That's why you need probabilities. Okay, if I put threshold of 0.1, what would be the reason? What would be the sensitivity, specificity, both positive rate, both negative rate? No. Okay, we are in logistic regression. Forget about linear discriminants. You don't know yet this linear discriminant yet. Just forget it. I want, now I'm just preparing my slides. Yeah, but it's now as I I'll resend it later with this correction probably. You just have to do it once and then you can run any module. Of course, you will be copy if you the only problem can be if some so understand where the probabilities are. Sometimes the model would do. Okay, now we have it. You see, this is this is the model. This is the model, logistic regression. So we predict classes, we predict probability. Actually, you don't need this. New data is in redundancy unless we don't use it. It just is, or you can just provide the data you predict. So predict classes, predict probabilities. The only difference is type props. And now pay attention how you use confusion matrix. So in confusion matrix, your data is your predicted classes. Reference is what you observed, the real classes. And positive is how the class is called. In our case, it's successful. It could be class 1. It could be any label. You just have to explore how the classes could be 1, 2, could be 20, 30. This is what you have to explore. And then, but for the walk curve, you need responses class, predictor is probability. Here is probability. And this is our predicted. If you type how the LR probability looks, you will see that this is a table with the 2 columns. One column is a successful probability. The second column is an unsuccessful probability. And that's why we address successful. This is level, and level. So the first and third arguments are the same. Then you plot and then out. That's everybody. Everything is done. This is a block of code. I would like you remember somewhere copy between dollars or signs or whatever. So because to run the next model, you just copy it and you substitute the methods. Probably it is better to rename. And here you replace model, you replace name, you replace things here, and you have again the matrix. This is the block. That's how we will everyone. Maybe we will try different data sets, reduced or full set, depending on the data. Okay, tell me who managed to run this finally. That came in here.
Yeah.
So, did you manage? No. Was it 0? What's wrong? And you give them up. Does it work? And you too? You manage? You manage? What about does it work? Does it work now? So let me see the question. Okay, it does work, right?
How is it going? Работало?
У вас? Okay, so I'm sorry for skipping the break. So let us decide, shall we do it now or we continue and finish earlier? What would you? Because it's almost 8 o'clock. Huh? Continue. Huh? Or you can go back and forth. Or making a break. Vote. Who are for continuing without a break? 1, 2, 3, 4, 5, 6, 7. Who would like to have a break now? 1, 2, 3. Okay, so democracy. We continue. You can go out. We do now LDA, linear discriminant analysis. So, does everybody just finish with this? So we have a goal. Now life is easier. Oh, let me write down the numbers. Please write down the numbers. Please write down the numbers. What are the AUF on the test set? Huh? Who will tell me the numbers?
Not 9.
How many?
Not 9.
Just not 9?
Not 9. 0 plus 7 and 8.
0, 7. Let's use 3. Does everybody have the same number? Okay, accuracy. It's you go to the confusion matrix. 0 point what? 88? 83. Sensitivity. Sensitivity. 783. 783. 0.869. 0.869. So specificity is not good. So we are not really recognizing well the second class. Okay, so there is some modeling was done. The next model, linear discriminant analysis. Okay, first let me acknowledge, I'm afraid you're not really susceptible to the theory now, but still, linear discriminant analysis. You just everything is the same. I don't know, probably it's also quick LDA. You have the model, now you do predict. You do the same and tell me numbers. Now it should be quick. Because you just have, you predict classes, you predict probabilities, and tell me numbers. You predict classes, you predict probabilities, and tell me what the number is. And then I will tell you in exchange what is the linear discriminant analysis. So how's it going? Is it fast? Maybe? Or not? So running, so you can have a break while this is running. Did it finish for somebody? LDA. Actually, I can now tell you what it is, because the only thing you have to copy the block, replace LDA, and then let me tell you what it is while it is running. Let me tell you what it is while it is running. Because these are new, we did not have the, well, logistic regression is kind of analogous to the linear modeling in regression model. It's logistic regression. But linear discriminants, we didn't have this in regression. We didn't have it in the regression. Linear discriminant is based on the bias theory. You should remember the conditional probability formula. Conditional probability formula is symmetrical like this. So the if x probability of x on condition that y happen multiplied by probability of y is equal to probability of y on condition that x happen on the probability of x. And while having this formula for conditional probability, it can be written in the form of the bias theory. So when you have conditional, which we call a posterior probability, so the probability of x on condition that y happen is a prior probability of y and conditional probability of y on condition that x happens. So how does formula relate to the classes? Easily. So for example, we have the this is the formula for population probability. So that's this is a probability that the sample x is belonging to the class that we predict. So in general, I write it down with the L, not just presuming that we have a number of classes, not just two, but any number of classes. So this is a probability that the sample x is a member of class C. This is class. So probability of class depending on the sample. That's what we predict. We predict probability of a class, and here is our sample, and sample X is a set of predictors. 2,000, 3,000, 10,000, whatever you like. X is a vector, and this is just class. So when you insert values, so this is how it will be calculated on machine for you. Now it is calculated according to this formula, right in this model. So this is prior probability of member in the class. Here this is prior probability. And this is what we replace with a conditional probability of observing predictor X given that the data is from this class. Conditional here is from our trained data. So we have our trained data, and we can estimate these probabilities from data, or this would be the frequency of the data observing to the class. And the idea is to minimize probability of misclassification. So here is the more natural example. So you have some data points and they have distributions. Of course, all the data, if it is number data, have some distribution. Let's see, we have class 1 and just one predictor for simplicity, not 2, not 10, not 1,000, just one predictor. And this is the data is somehow distributed for the class 1. And for the class 2, this data is also somehow distributed. And you see this distribution overlaps at certain points. So when the predictor has this range of values, it could be class 1 or it could be class 2. But because there is a distribution, and probabilistic distribution, we always know probabilities. We always know probabilities of this particular predictor belonging to this class, just based on one class. For example, if you take this point, so imagine this is just some normalization. This would be the probability. This would be a probability when we have predictor equals 6, that would be probability to belonging to class 1, and this would be probability to belonging to class 2. We can see that the probability to belonging to the class 1 is bigger, higher than the probability of belonging to class 2. That is why we vote for the class 1. We say, okay, if the predictor has the value 6, let it be the class 1. This is just how we decide on the class. So this is what is now I'm going back and see when we have this probability of being the class star, we decided if one probability is higher for one class than the other, then we pick up the class with the highest probability. But there is in linear discriminant analysis, there is a drawback. Drawback what? First, the assumption that the data follows normal distribution. So all this, you know, when we have predicted data, and it is not the case. And there are different means for each group. So there is no big overlap between, because if the means are different. Means are different for different groups. Sometimes it does work, so that's, but these are assumptions. The good thing is that it has an explicit formula. Once it's normal distribution, and here is we have to find the linear distribution again of the variable. That's why it's linear discriminant analysis. So discriminant analysis, we discriminate between classes, and linear because we assume that it is the linear combination of predictors, and we should find this linear combination that would maximally separate two classes, because there will be always overlapping areas. There will be always overlapping predictors, when with the same values of the predictors you cannot decide to where to go. Here is, for example, the examples where you can do again. Remember with these PLS would be this good analogy. With the PLS and regression, we search for the transformation of the axis when the classes are clearly separable. The same here. For example, if you have dependencies between predictor A and predictor B, you can always find this vector, say this rotation in space, right? When you do use this new system of coordinates, all the projections of class 1 and all the projection of class 2 groups as a point here or here. You see, this is a new projections on the new axis. And new axis, we call it discriminant vector. And they are easily separable. Easily separable, meaning you can draw a line. There is a line boundary between the classes. And here is the task. So then it is easy. So you do the linear transformation of split. That is why we used pre-processing, data pre-processing normalizes scaling. So with all this PCI thing, we always usually do normalize and scaling procedure. That's what we included in the modeling. Did it finish, by the way, or not? Did it? Good. So that's just on the field. Let us see what did you have. This is what I have. It's on my model, but it's could be for the train test. Let me see. Did you? So is it finished for everybody? The modeling, the LDA, or not? Huh? Yes? So did you predict? Tell me the numbers. Tell me the numbers. Okay, I'll look for LDA.
Don't like to do.
Okay, and the third number? Would be useful.
Well, viewers is not 85. 85.
3 digits up to the top.
2 digits. 85.
There
3
is no-
digits. 85 9. Or 84 9. So it's
849. And for the AUK, 3 digits?
1 is 1.
9 to 1?
9 to 1.
Okay. Sensitivity?
Those 8 to 5.
The word 8 to 5.
And those 863.
863. I want you to have this number written somewhere for all the models, because we have to compare the models. I want you all the numbers be written, and because next class we will continue. Somebody has to tell me the previous number because we continue the modeling. Yeah, I guess so. This AUK is on the training, so not on the test. Did everybody manage to run LDA now? Just copying the block and replacing modules. What was the number? Okay. Do I have this LDA model in the package I provided? Or no? Because we are approaching the models that we won't run the model themselves. We will be uploading it from my package because it takes too long, but you will do yourself predictions. Do I have LDA model in the package or I don't? Because I expected something much more. Who can tell me if I have it? If I don't. LJ, look at this package. You will see now the package, this grand data package will be containing already pre-computed models. No LJ. So you see there are neural networks, support reaction machines, but there is no LJ. Well, because LJs, I expected it should be done in the class. It should be done in the class. Who run the LJ module? Can you raise the hands, please?
Training.
Training is finished. Oh, so it does finish. So it took approximately what, 5 minutes?
Oh yeah, about 5 minutes.
Yeah, that's 5 minutes. So 5 minutes is reasonable. So did you able to predict and build confusion matrix similar to logistic regressions by copying the block?
Yes.
But to make sure you do not use the number from logistic regression, you have to replace, right? Sometimes, does probability vector also probability prediction has a table with a successful columns?
Yes.
So the same. Let's see what is the object of the probability, because you have to know what should be predictor is the probability. Polarities or is that's why better to rename the but this is a logistic regression. What about LJ? Okay. LJ is probability. Okay, that's good. Then when the object of confusion is LJ for LJ? I don't see it. There's none. Important, that's what I thought. There is a block. Where is your block? That's the response. Since you kind of did it somehow, you start from here. This is your first. No more currency. Okay. You copy into there, you just LR, replace LR with and just have the same logic. Okay, who has problem of running confusion matrix on? What else? It's actually, you see what happens, that's why. So this is what we have. As a result of this linear discriminant, if you plot linear discriminant scores here, you see that at least those that inside this, half of the data here are clearly separated, could be clearly separated by successful and unsuccessful. So you can plot this discriminant value, that's why it's discriminant. There is penalized model. Let me try. Maybe what time is it? Okay, I promise we will finish earlier. Okay, let's run the next one. Okay, That was linear discriminant. What's next? PLS, what is next? Partial square discriminant. Partial discriminant. Again, what is a block? Now partial least square. So what we do a transformation of. Do you remember what are the partial least squares do in regression? How do we do this transformation? Who remembers? Huh? No, PC is PCF. Partial least square. PLS. PCA we do not take into account outcome variable at all. We just reduce dimensions. And on PLS we again do linear transformation of the predictor space, but we look for the transformation that in regression that correlates the best with the outcome. Remember? Okay, you will be right. You have to remember. And here, you can do the same transformation that would correlate with classes prediction. And this is the number of components to take. So we reduce the space. We do transformation and we reduce the space. Okay, try, run, and predict. Try and predict. Here is that it does variable importance. I need numbers. So now we have PLS. So we did logistic regression, linear discriminant, now partial least square discriminant analysis. PLS, I need numbers. I need numbers. So now it should be easy. You just copy blocks, replace, say, LR or LDA with some. I would suggest you change the names. Otherwise, accidentally, the prediction from logistic regression can enter into your function. It won't be confusing. So it's better to rename it. So if you say, does it take some time to run? Михаил. Никита. Здорово. Илья. А он здесь, он ни разу не был. Он так не учится. Павел. Матвей тут. Матвей, нет, Матвеев. Кашкин Матвей тут. Так, вы ему тоже передайте в эту Илье, да, что когда придет сдавать, чтобы со всеми таблицами рассмотрели. Михаил Кремлев. Екатерина. Лев. Василий. Александр Пискин. Ой, нету. Ой, нету. Артем тут. Марина тут. Ирина тут. Мамусаид тут. Ирина тут. Валентина тут. Елена. Ой, наша. Ну, как-то что-то особо ничего не получилось. Левчик переход. Или Артемий. Артемий. Артемий тут, не тут? Нет. Кристина. Okay. So, what about the PLS? It is finished? What are the numbers? What are the numbers?
First two is the same.
Exactly the same? 91? Maybe you just didn't replace? Did everybody get the same number?
First two is the same. Third and fourth is other.
Okay, what are the first and fourth?
841.
841, so 16 first. And
854.
854. So you also please copy it somewhere, this number. I need it. I need that you have this table with numbers for yourself to continue with exploration of the model. If you plot it, can you plot it, PLS kit? Will it show you the tuning plot? If you plot it, plot the model, PLS kit. Will it show you the tuning plot?
Yes.
What's the best number? It's number of components, right? Yeah, so it's always increasing. That's why, so the more components, the better it is prediction. Okay, there is another thing with this model that can do, it can do variable importance. Variable importance, you can use a var INP function and see what are the importance variable. Let us do a little bit of analysis of the data. So we're predicting which factors affect success of the grant, and here there are, so you have to give an answer. You see the month of January, actually it's the 3rd, as we observed it already as log odds ratio. So it's also fell out here. Contract value band somehow. So grant category, some grant category. Though unsuccessful CI, you see unsuccessful chief investigator, so number of unsuccessful grants previously from chief investigator, also among the factors. Then, month of August, you see January, August, somehow August is, before September, August is a holiday month.
So these are all, why is it these groups?
It's, no, I don't think, it's just, it's not an absolute value of the coefficient, I guess. Those scale falls should be, seems like positive, seems like positive.
So better is the unsuccessful.
Yeah, it's interesting. Tri-scale true, and then you have 100% scaling. Tri-scale true, so it's not a scale false gives you the absolute value.
It's the same, but
The same, but its contract value band is 100%, and then it's all, right?
yeah.
Yeah, and so it goes down by. Okay.
This is for
I see. So this is always interesting analysis to look at. And variables importance for that is interesting. Unsuccessful with a positive contribution. Okay, I think it's enough modeling for today. And we release away. Yeah, we can. What is this? This is the, it's actually a penalized model. We can look at Mmda. Penalized series function. We can run it. Hopefully next class we can run everything faster, because for that I should have provided, so you don't have to actually to run it, because it took 1 hour, 5 minutes on 3 cores of my computer, my desktop. But there will be data providing that you will be just load. So for the next class you need all the data, because there will be there will be neural network models, SVM models, which so what you do? For those who like. So actually last class, the next class is the last class and workshop. And then if you're ready to write an exam, you're welcome. On December 24th. So if you don't have questions, then we finish that. Okay, I don't send it around. No, I don't, of course. the basic understanding, say, to be able, so if it's neural network, to be able to draw this scheme and see what are the ways, what's finding what. So it's not, I do not think that's the math, no, but the general idea behind this model. If you can provide the formula it's a rotation of the in space. And rotation is a linear and what we look at that both so I would just say it's hard.